Part A states under standard conditions at 25 degrees Celsius, solid zinc reacts with aqueous copper 2 plus to produce solid copper. In Part I, we are asked to write the balance equation for the half oxidation reaction. Oxidation means the element loses electrons and has a more positive charge when on the product side compared to the reactant side. If we look at the equation for the reaction, we can see that the charge of Zn goes from 0 to plus 2. Because in the increase of charge, therefore Zn is being oxidized. The half oxidation reaction is solid zinc plus 2 electrons yield to aqueous zinc 2 plus. In Part 2, we are asked to write the balanced net ionic equation for the overall reaction. The balanced net ionic equation is solid zinc reacts with aqueous copper 2 plus to yield aqueous zinc 2 plus and solid copper. In Part 3, we are asked to calculate the standard potential for the overall reaction at 25 degrees Celsius. To do this, we take the half reactions along with their standard potential. We then flip the anode so it can cancel out the electrons and match up the overall reaction, which therefore flips the sign of its standard potential as well. To find the standard potential for the overall reaction, we subtract the anode from the cathode and get 0.48 volts. In Part B, we're given at 25 degrees Celsius, H2O2 decomposes according to the following equation. 2H2O2 aqueous yields to 2H2O liquid plus O2 gas, and its standard potential is 0.55 volts. In the first part, we are asked to determine the value of standard free energy change, standard delta E, for the reaction at 25 degrees Celsius. To do this, we use the equation standard delta G equals negative number of moles of electrons times Faraday constant times standard potential. To find the value of N, we look at the half reactions equation and see that there are 2 electrons, therefore N is equal to 2. We then plug in the numbers into the equation and get standard delta G is equivalent to negative 2 times 96,500 times 0.55, and the standard delta G of the reaction is negative 110 kilojoules. In the second part of Part B, we are asked to determine the value of equilibrium constant for the reaction at 25 degrees Celsius. To solve, we use the equation standard delta G equals negative RT ln K and rearrange the equation algebraically to isolate the KEQ value. After we plug in the values, with this we get 2.0 times 10 to the 19th for our KEQ value. Part 3 tells us the standard reduction potential for the half reaction O2 gas plus 4H plus aqueous plus 4 electrons yields to 2H2O liquid has a value of 1.23 volts. With that, we must determine the value of standard reduction potential for the following reaction, which is O2 gas plus 2H plus aqueous plus 2 electrons yields to H2O2 aqueous. Using a standard reduction potential chart, we find the other half reaction and find both the standard potential values. These two values are combined to find the overall standard potential. The answer is 0.68 volts. In Part C, it tells us in an electrolytic cell, solid copper is produced by the electrolysis of copper sulfate aqueous. We need to calculate the maximum amount of solid copper that can be deposited by a direct current of 100 amperes passed through 5 liters of 2 molarity copper sulfate aqueous for a period of 1 hour. Using stoichiometry, we can convert from hours to grams. Using what we are given, we can take 1 hour and divide that by another hour and multiply that by 36,000 seconds and divide that by 1 second, multiply it by 100 coulombs divided by 96,500 coulombs times 1 mole electron divided by 2 moles electron, which is the number of electron moles in the half reaction equation, and multiply that by 1 mole copper divided by another mole of copper and multiply it by the molar mass of copper, which is 63.55 grams. With this calculation, we get 119 grams of solid copper.